Hi, I am Amber Horvath, and today I'll be presenting our paper, Meta Manager, a tool for collecting and exploring meta information about code. Software engineering is a discipline about information management. When developers are attempting to understand code, they must grapple with many questions and information management tasks, with one of the most pervasive and difficult questions being, why is some code written a particular way? Also called the Today, in order to answer this type of question, developers must recreate the context in which the implementation happened through revisiting the code history or asking their teammates. However, both of these strategies often fail if the code history does not include any information about why a particular decision was made, which is often the case for lower level details. Asking teammates can fail if the team member is no longer on the team, does not remember, or is busy. Nonetheless, developers have and will continue to have to reason about rationale behind decisions when attempting to come up with a modification to some code, reason about behavior, or attempt to debug. Prior research has highlighted this challenge, citing that this information is rare, gets lost frequently, is exhausting to understand, and a common information need for developers. Furthermore, these questions of design rationale are just one of many challenging questions developers must ask themselves when working with unfamiliar code. Developers must also often reason about how the code has changed over time in order to design solutions that adhere to the goals of the system, what code is related to the code the developer is working with, and where the code originated from. Like questions of rationale, these questions often do not have answers that are readily apparent purely by looking at the code. The answers to these questions often have implications for the resulting design of any further code, and reconstructing the history to attempt to answer them is laborious if not impossible. These are also importantly questions that AI cannot answer currently. We address this challenge of reconstructing code-related development information for question answering with our tool Meta Manager, a Visual Studio Code extension for TypeScript, along with the supplementary Google Chrome extension. Meta Manager is designed to support answering questions with the following design goals. The first goal is to automatically collect and organize code history information, including not only code versions, but information about the code's provenance, such that developers no longer have to manually attempt to reconstruct this history themselves. Second is to support challenges of scale, given that large-scale projects will comprise thousands of code entities and a multitude of edits across time, through using a visualization for summarizing both large and small histories and prioritizing certain types of information. Lastly, to make this potentially large set of history actually useful, Meta Manager supports navigation by using interactive mechanisms for traversing through code histories. We can see how these design goals are instantiated in the following demo. In our study, we had participants answer why a particular method, parse HTML, was replaced with a different method. We can recreate this question using the Chrome extension. We can capture that the developer searched JS DOM not working with Canvas, and capture the code that the programmer copied from Stack Overflow. Once pasted into Visual Studio Code, the code history timeline, which displays how this particular block of code has changed over time, will update with this new interesting editing event. Our system displays this code history through a visualization and, for each version, meta information. The visualization depicts code block changes over time, with the x-axis representing code versions that the Meta Manager logged, with the orange scrubber showing where in time we are, and the y-axis representing how the code grew, shrank, and moved. The colored areas represent code blocks, with the large blue area representing the extract snippets arrow function, which is in extractor stackoverflow.ts. The right side of the pane displays information about the code history at a point in time, including the version number and additional meta information, including the time that they were edited at, additional information if the code is an editing event of interest, and the code at this point in time. For later developers, including all 7 participants in our study, this historical information about the code version can help explain why some code change happened. The system displays the user's coding-related search query, the part of the code that was pasted from online highlighted in blue, and captures both a copy of the original relevant part of the web page that was copied from, in case the link or its contents change, and a link to the original source. This capture of the web page can then be viewed within Visual Studio Code so the user can better understand what happened.
The system does the same capturing of web data for ChatGPT and GitHub, both of which can also be viewed within Visual Studio Code with appropriate contextual meta information, such as repository details or thread titles for ChatGPT. With this information, future developers can understand that the API methods were swapped due to an issue with the Canvas element. Developers often want to know how code evolves over time. Our system makes this history navigable to help developers better answer this question. This navigation can be done using either the scrubber for quickly moving between code edits or with the annotated labels along the x-axis, which denote editing events of interest. With the scrubber, the code stays in view so developers can move through many edits at little cost and see how some code has changed. Our system then helps with the scaling problem by pulling out events that we hypothesize to be more interesting, such as copy events, paste events, and events in which code was copied from online. Users can see these events by clicking the labels to navigate to those versions. Along with why some code was introduced or how it changed, developers also want to know where code came from. Our system helps answer that question through clarifying the relationship between copied and pasted code. For example, this code was pasted from a different file. In this case, an arrow function in the file extractor github gist.ts. The preview shows how the code in the arrow function looked at the time of the copy and can be seen now by clicking the arrow function link. When investigating some code, developers may want to drill down to a specific line to see how and why it changed. Meta Manager supports this through searching forwards, backwards, and across time for when some particular code has changed. For instance, as part of the parse HTML question, developers need to know what code parse HTML replaced in the past. This can be done by selecting the code in the editor, since the editor represents the most recent point in time, and then searching backwards by using our search action in the context menu. A timeline updates with annotated instances of when the searched on code was edited. Clicking through these search results shows constock was previously set to JS DOM, with the Stack Overflow post providing some more context as to why that switch happened. If a user finds a code version and are curious how some code changed after that point in time, they can select some code in that version, then click Search for selected code. To further support drilling down on code and dealing with the scaling problem, developers can filter to show only events of interest, including copy events, paste events, and events with online code, by clicking the relevant filter buttons, which will update the timeline to only show those events. If a developer isolates a particular area of interest on the timeline, they can either move version by version through using the arrow keys or by zooming into the visualization. To zoom, the developer can set the scrubber at the beginning of the slice of history they want to view, then hold down the Shift key and click where they want the zoom to end. This view allows for more fine-grained scrubbing and viewing of events and can be dismissed by clicking Reset Version Range.
In our design of Meta Manager, we sought not only to provide functionality that supported each design goal, but also to provide information that could be used to meet developers' information needs. For resolving questions of design rationale, we hypothesized that developers' search queries and copy-pasted code could be used to answer these implementation questions when contextualized with proper versioning. An inexplicable implementation choice or hack may make more sense when one understands what the developer was originally trying to accomplish, which can be conveyed through web activity and usage of AI programming tools. Returning to our other information needs, for surmising code history, we support both macro and micro levels of investigation through versioning and supporting interactive mechanisms for navigating through those versions. Significant edit events, such as commenting out code, can signal when a change in implementation direction has occurred. And scrubbing through a block's history, along with viewing its history in the visualization, can give a quick overview of how the code grew, shrank, or moved. For a micro-level view, developers can select a code snippet to search on across time to see, for example, when a variable was renamed. In understanding code relationships, identifying copy-paste connections can be a fruitful avenue. If code was copied and pasted around, that is a strong signal that the copy-paste patches are related. So we posit that investigating those versions may help with understanding otherwise invisible relationships between code patches. We further hypothesize that this can help with determining code locations to update when introducing a change. Using the code visualization may also help with determining when a code is commonly edited together, which can be a signal for understanding a developer's working set of related code patches. Lastly, for reasoning about code provenance, or where some code came from, the same relationships of copy-pasted code, including code sourced from online, can be leveraged. As more code is sourced from AI models, the more relevant this lineage of code history and its provenance is likely to become. To evaluate MetaManager and whether it supported question answering about code history using meta information in the ways we envisioned, we ran a small user study. Participants were tasked with using MetaManager to answer 8 questions about an unfamiliar code base. These questions were derived from previously discussed information needs relating to code design rationale, history, relationships, and provenance that would be otherwise unanswerable without MetaManager. We additionally wanted to evaluate whether our scaling and navigation techniques in MetaManager actually supported developers in comprehending and finding code versions of interest. This artificial code base that we created included edits of interest, such as copy-paste from online sources, and many versions that participants would need to forage through in order to answer our 8 questions. Each question asked during the task was based upon a question reported in prior literature that related to an information need we were interested in addressing. Each question had multiple steps that needed to be completed in order to solve the question so as to not make answering the question trivial, and participants were given 10 minutes to answer each question. On average, participants were able to use MetaManager to successfully answer our code design and history questions around 86% of the time. Each question took on average 4 minutes and 52 seconds to answer. Questions Q3, Q4, Q5, and Q8 were all answered correctly by each participant, and no participant got less than 6 answers correct, suggesting that the MetaManager was successful in supporting developers' question answering with respect to the information needs we were interested in supporting. To understand how exactly MetaManager assisted in participants' comprehension of the code and its history, we qualitatively explored how participants used the various features in MetaManager to answer each question, paying particular attention to how well these features worked in support of MetaManager's design goals. One of MetaManager's design goals is to automatically capture and provide code history and provenance data. Participants reacted favorably to this information, especially in the case of code sourced online or from an AI system. This preference influenced their question answering strategies, with most participants defaulting to selecting web events on the timeline, especially if they did not know exactly what to do next. P4 clearly articulated this preference when answering Q2, stating, "I'm looking at ChatGPT because that worked well last time." With respect to our goal of scaling large amounts of information, we partially have support that our mechanisms worked just purely given that participants were overall successful. Qualitatively, participants used a combination of various features, including the visualization, zoom, and timeline annotations as a way to create smaller, more manageable sub-histories to explore, given their understanding of the code history. In supporting navigation, participants overall were able to successfully navigate in order to answer their questions, but faced some unique challenges inherent to supporting navigation across multiple axes, leading to some design challenges and opportunities. Improvements to MetaManager may include supporting summarizing potentially large sets of code history to further showcase code evolution, and allowing for composition of code versions across both time and space as participants struggled when navigating between these more disparate code versions. In placing MetaManager in the larger context of code comprehension tools, we can look to other information foraging and sense-making works related to code. A related work looked at how developers search for variance among a large set of code versions and found that developers often think of this process as building a story of the code history. Our participants similarly commented how they were able to piece together a story of the code through the provided meta information, especially with respect to the reused AI prompts and search queries conveying high-level authorial intent. With potentially more development shifting towards using prompting to write code, systems that allow for the exploration of code-prompt relationships in order to reason about code evolution and design are likely to become more important, with MetaManager beginning to probe on this research thread. In developing tooling to support the comprehension of AI-generated code and code prompts, this implies a need for tracking AI code provenance, which MetaManager supports. Tracking AI code provenance has already been cited as a paramount research need in order to support answering questions such as how correct some AI code is and how long does AI code persist in a code base. We showcase MetaManager as a system that allows for the answering of these sorts of questions while also showing that using AI code generation, meta information can support other activities such as reasoning about code design. Thank you.